Hey everyone, we'll get started in a minute or so. Um, all right, so today's topic is going to be attention and transformers. This one's especially cool, I think interesting, because it kind of sets the pace for the rest of this course. There's a lot of really important current computer vision techniques that use attention and transformers, and that kind of trickles into a lot of the next couple weeks of content that we're going to be covering. I hope you enjoyed last lecture. Today we're going to be taking that a step further, explaining some of the problems with recurrent neural networks, and how we can sort of think of approaching solutions and how those solutions have evolved over time to produce what is one of the state-of-the-arts in that transformer neural networks are being used. With the rise, especially of like really large language models like ChatGPT, GPT is a generative pre-trained transformer. So we'll be learning about kind of what makes that tick. And this is applicable to a bunch of different tasks. So why attention? We want to be able to focus on certain parts of an input. So when we make predictions about something, for example, identifying an object or predicting the next word in a sequence or doing tasks that are sequence to sequence translations, we want only a subset of the features given. So this saves processing time, and it also makes us yield better predictions because not all features are equally as important. Quick case study. We can remember that RNNs or recurrent neural networks process sequences step by step, right? There's almost like a feed-forward neural network that's rolled out over time, word by word, by taking the previous hidden state as an input in addition to the current token and using that to make some informed decision for a future state. Vanilla recurrent neural networks have trouble with longer sequences due to the vanishing or exploding gradient problem, right? There are vector to sequence models, things like going from an image to a sequence to vector models, things like going from a sentence to like some sort of sentiment value, and sequence to sequence models. These are for things like language translation, things like that. RNNs are able to approach these kinds of longer horizon problems, but they're slow to train, right? We do some form of like truncated backprop, and they can't deal with long sequences very well. These lead to exploding and vanishing gradients where we're multiplying very tiny values that are less than 1 together. And these values naturally will get pushed to 0 as you multiply them across a very, very long sequence. The solution to that was LSTMs. Looking at specifically sequence to sequence models, we can encode sequences as fixed length vectors. As you can see, we have a source sentence that's an input where each word is some kind of fixed length vector. Then we're trying to decode this to another sequence. So we're trying to produce another set of vectors that represent the ending sequence. This still has memory issues, right? We're encoding long sequences into a very fixed length vector. And because of that, these are being stacked across our entire sequence. And this can lead to a lot of sequences that are long and not super computationally feasible to compute. We're going to look at a specific example and kind of stick to this, translating from French to English. We can notice in the little correlation matrix in the bottom right that there's a nice correspondence between words of both languages, even if these aren't one-to-one. These are kind of like the similarities between translations. So as you can see, destruction maps to the French word for destruction, de maps to the, and things like that. These values, equipment maps to its corresponding word in French, and this shows us that this is, a very plausible step that we can take. There is some mapping that exists that approximately gets us a translation we might be happy with. even if it's not perfect. Now, what if we reference the input sequence directly, right? We have a certain sentence, say like a French sentence that we're trying to translate to English. We can use the information in the French sentence to hopefully get some more information besides just the embeddings that we get, right? We're able to search through this entire sequence of information that we have, and their order matters and their constituents matter. And we want to take that into account when we're predicting, for example, the translation. We can do this by looking at specific relevant input tokens. If I have multiple sentences, perhaps only the last 5 words will correspond to the 6th word that I'm trying to predict, right? So these might be more relevant implicitly than a word that came like 2 sentences ago. We want a way to be able to model that so that our model is able to understand that certain sentences, certain words, certain parts of words are more important than others. How can we implement this? Approach 1 is something called hard attention. This predicts which indices are relevant when trying to decode at a certain time step, and we use those as specific inputs. You can think of this as kind of a way of feature selection, where we're selecting specifically which indices are relevant. But because of the nature of this feature selection, it's a difficult problem to backprop through, right? It selects almost a single element to attend to, and this is non-differentiable or not easily differentiable because we're making a discrete decision about whether to use or not use a certain part of the input. This is, however, pretty computationally efficient compared to our second method, which is soft attention. Here we generate a set of soft weights. For example, we use softmax to generate some kind of distribution over the input tokens that shows us what the relative importance are to each other. In this way, we can do a sort of weighted sum where we're taking all of our inputs into consideration, but we've run some kind of softmax function over it to generate a distribution representing how important different parts of our input are to our output. And this is something that can be changed over time. This is something that's specific to different parts of the sequence, perhaps. And as this distribution changes, so does the way that we weight our relative sequence. The advantage of this over hard attention is that it's differentiable because it's a continuous distribution, and it intuitively combines representations of multiple relevant features, right? Instead of like kind of a 0-1 classification of this word is important and this word is important, I can say, this word has a weightage of 0.5, this word has a weightage of 0.4, and all my other words combined have some weightage of 0.1, right? So relative to these 2 words, they're not that important. And now I also have a relative weighting of how important these 2 individual words might be to my output, right? So this gives us a lot more information. And intuitively, as humans, as we look at sequences, we can see that, we're not necessarily making binary decisions or discrete decisions, but we're kind of taking everything into account. When translating destruction to the French representation, what input tokens are the most relevant? We want to reference la destruction, where the attention weights might be, like I said, 0.4, 0.5, and then zeros for the rest. And here, when we're trying to produce an English output, and we're trying to reference our, sorry, this connection seems to be not the greatest. When we're trying to represent a specific input, we can realistically take into account 2 different types of inputs because of this distribution. And so now we can use the combined feature vectors of la and destruction. Now, having seen destruction of what's the most relevant next token? Now we want to reference the French word for equipment and predict the distribution of feature relevance. Again, if we have a softmax, this is something where we can find soft weights over the features, give the weighted sum to the model, and hopefully equipment is given a higher priority. Diving a little more into soft attention, think of it as a differentiable database lookup, right? We have a database of every single word, and we're assigning essentially a weight to it. And depending on that weight, we're factoring that into our output decision. We have a database of features we're interested in, right? Which is our French reference sentence that we're trying to translate. And we want to use a subset of those features to make our prediction. So decoding the English translation or something of the sort. We have our database of features, right? This is our initial French sentence. You can think of it as like our initial vocabulary. And we want to find a way to intelligently reference certain parts of this sentence to make our final decision. We know that we're able to embed these into a representation that our model can take in into some dimensional vector, d-dimensional vector. Certain models like BERT will produce like 768 dimensional vectors. Other models like Glove might have 50 dimensional vectors, and this choice can vary depending on your use case. Now we have some model. This is no attention, just an RNN. We have a start. We have our first kind of token that we're looking at, which is the representation of law. And we're trying to come up with, what is potentially our next word. At time 1 or the next step, we're looking at destruction. And we're taking this into our hidden state, into our next state to try to predict, all right, what does this realistically map to based on our database of features? How can we do this? We already predicted destruction of the, and now our target word is equipment, right? We have our last token, which is the, and we have the representation that we've produced, right? Which is this vector over here. We're trying to see, how does this model relate to our database of features? And we want to see, based on our database of features, how can we intelligently determine that the next target word is equipment? This is what our RNN has spit out after some I time steps and some hi-1 hidden states previously. And we can do this by taking this representation and doing some sort of lookup, right? We look at our hidden state from before, which is some embedding that we've generated, and we look it up in relation to our current database. We have already embeddings for each, you can think of it as a vector in our database. And by doing some sort of comparison between our hidden state and our database, we can figure out which is the most similar and which one do we want to kind of incite a higher weightage towards. We can do this using some sort of similarity metric, for example, a dot product. And this results in a distribution based on the magnitude of the dot product of some hidden representation and our database. We can treat this as a distribution. We see that the highest dot product is equipment, or the French word for equipment. So that's the most relevant to the next token that we're trying to predict. We can now pass that into our RNN and use that for future hidden states. We take a weighted sum, and we use that information to kind of bolster the way that we're predicting our next token. We can think of this, like I mentioned, as a differentiable database lookup, where we have some database of features that we're interested in, and we want to use those features to make our prediction. We're doing this lookup using a dot product, and there are different kinds of ways that we can do this lookup, and the retrieval is a weighted sum. So we're taking our keys, we're doing some sort of lookup, and then our values are a weighted sum of the different values that we've come up with, where the values are the result of the dot product. And this weighted sum is based on the values, which are now implicitly weighted based on our dot product. Now, what is a metric to decide how this lookup should happen? There's a relative importance of similarity or relatedness between some sort of like implicit representation that we're trying to tie to our concrete feature data set or database. How do we know we're looking for the French word for equipment? Based on the current decoder state. There are a couple ways that we can do this. Here, SI is the decoder hidden state or the query, right? So you can think of this as what we currently have. And HI is the encoder hidden state or the keys. For each SI, we want to find its relevance to each HI, where in this case, the keys are, maybe what we're trying to find. Each resulting score, let me move this up here, is passed through softmax to get our final weights. These are a couple of different ways on the left that you can score alignment between an SI and an HI. There are different ways to do this. There's an additive method, there's location-based, which uses some extraneous information. Dot product, which we talked about earlier. There are a couple of different ways that we can do this comparison. Now onto the retrieval step. There's a weighted sum of representations that we now want to consider, right? And we want to update our values accordingly to assign different weightages based on the result of our dot product or whatever similarity metric we use, right? In other uses of soft attention, we sometimes just want to concatenate values instead of taking their weighted sum. And through that like concatenation, you're taking into account potentially their respective values. But for now, we can look at a potential model that came out earlier. That was the first paper to use the attention mechanism. It's similar to the previous example, except instead of this dot product lookup, where we're taking the dot product between our feature database and our representation, we're using something called additive attention. What additive attention is it uses some sort of learned set of parameters to compute an attention score. So it can use like a feed-forward neural network, for example, to calculate the attention score, and it uses these learned weights to then normalize and get a distribution. As opposed to that, the dot product, which is the example we specifically looked at, is really simple, computationally efficient, doesn't involve learned weights, and doesn't have like learnable parameters. But Bodenau's model in 2014 was using this different kind of similarity metric that used learned parameters. This also uses a bidirectional LSTM, right, where we have like some sort of forward and backward LSTM that goes from left to right and right to left to incorporate both like past and future information in some sort of like input representation. Now we're going to talk about attention for vision. I can pause for a quick second and ask if there are any questions about soft attention. All right, cool. And feel free to raise your hand if there are any questions that come up. We'll now talk about attention for vision. And as we've learned, attention is simply a means to look up features, right? We want to prioritize some features more than others. We want to select these features based on their relevance, and their relevance depends on the task that we're trying to do. It depends on our input data, and just in general, the fact that we are implicitly taking in more information than is particularly relevant. And we can apply this concept to vision as well. We can apply attention channel-wise to select which channel is most important. We can use attention spatially to select which part of the image is the most important. Maybe the top left is more important than the bottom left, right? And we can implicitly use attention in our architectures to select components of an architecture based on their importance. And we're going to talk about all of these. So channel-wise attention, we can use the case study of an SE net, or squeeze and excite. There's a problem with CNN layers, right? Which is that there's limited channel-to-channel interaction, and there's only local dot product sums between a filter that we're running over and our input. What we want is some channel-to-channel interaction that, as we know, our number of channels can scale based on our convolutional layers. We've talked about that earlier. And we want some sort of interaction to prioritize these different channels and these different implicit representations that we might be learning through our training process between features in the image, right? The squeeze and excite network is a way of applying this channel-wise attention. It's an attentional mechanism for computer vision. It's able to enhance different kinds of representations of different channels, or these like feature maps that we're learning by learning channel-specific importance weights. And the way it does this, the squeeze part is the first kind of mechanism that it uses, which is some kind of global pooling mechanism to get global descriptors of each channel, right? What this does is it applies a certain type of pooling, either like average or max pooling, that summarizes spatial information within each channel and comes out with a certain global value for each channel. And this represents almost an importance weight that indicates the significance of each channel's information in context of the entire feature map that we see, right? This represents, for example, kind of like a bird's eye view of each channel's content. And this specific value can be taken in context with every other channel's specific value to see its relative importance. The excite is the second step. Now that we have these weights, what can we do with them to ensure that these are being taken into account as we're processing a certain like image? Now we want to pass these weights that we've gotten in the squeeze step through an MLP, multi-layer perceptron, right, which we talked about in earlier lectures, to capture nonlinear interactions and rescale these feature maps using channel weights. The output of the MLP, is a set of channel-wise kind of scaling features that are multiplied with the original feature maps to rescale these feature maps by their channel. So we're taking our output, we're multiplying them by our original feature maps, and in that way, we're kind of scaling them implicitly to either emphasize or de-emphasize certain channels that our network has deemed to be more important than others. Again, this reweights feature maps, but it doesn't sum them, right? It simply does this multiplicative step. Spatial attention. In this example, show, attend, tell. We're trying to do some form of image captioning, where we take in an image, we have some sort of feature extractor with convolution layers. We have an RNN with attention over the image to figure out what is most important, right? Which features do we care the most about? And then word by word generation, where we determine a sentence that describes an image, that captions an image, and we can use the results of our attention or the most specific features that we care about to focus on specific words in our output sequence. This is a very classic kind of sequence to sequence task. Instead of French to English, we're doing image features to English. Again, there are two variants that we can use. We've talked about these earlier: soft attention, which is differentiable, similar to our previous translation example, or hard attention, which is not as differentiable, but we can train stochastically with certain sampling techniques. We'll talk about vision transformers in the next couple lectures, but we're able to model image representations by taking patches of images, having them attend to each other and passing this in as a larger sequence. We won't talk about this in this lecture. We do have a couple lectures about vision transformers, and they will be important as they've kind of dictated the state of the art of computer vision. There are different kinds of architectures that we'll also talk about in terms of these vision transformers and how they can get more complex and computationally efficient. I'll stop for a quick second and ask, are there any specific questions on squeeze and excite networks? I know this is a decent amount of content to take in, so feel free to raise your hand at any point if there's any questions in the middle. You can think of squeeze and excite networks at a high level, like assigning the same kind of distribution that we looked at in the French to English example onto channel weights. We're coming up with some sort of weighting using techniques that we know already, like max and average pooling, and we're applying them to each channel in our neural network. Squeeze is the first step where we determine those weights using the pooling, and exciting is the second step where we're passing them into some kind of neural network to capture nonlinear connections. We're introducing nonlinearity, and then we're multiplying it by our feature maps to weight them. And again, this includes learned parameters. All right, the next thing we're going to talk about is different ways that we can incorporate attention into our architecture, right? We can use attention to make informed decisions in our architecture itself, right? Soft attention can be used to determine whether to use a residual or convolution block, right? Which is more relevant based on the task, which is more relevant based on the type of input that we have. We can use attention to focus on one of the two. We can think of ResNets with attention, and this is a theme that we'll see later as well. But these kinds of architecture level attention mechanisms are used with LSTMs and in certain natural language processing applications. We'll talk about SKNets really quickly, where we can use attention to determine which kernel size to use. This is extremely cool because now we're using attention on each channel to select which kernel to use. This is kind of reminiscent to the inception model that we briefly talked about from Google's Google LayNet, right, which used multiple convolution kernel sizes in parallel. And now we're using attention to determine which one of these kernel sizes is more important, right? We can calculate importance with combined features, linear layers, and our softmax, come up with like a weighted sum for each channel. And based on that sum, we can weight which kernel size is most important. This allows our model to be a little bit more adaptive, right? we're able to select which kernels to use for each channel to potentially make it more effective in capturing information at different scales or patterns specific to each channel. We can see the model architecture below, how there's a split with two different size kernels of 3x3 and 5x5, and we can use attention to determine kind of which ones are more important. Now we're going to talk about self-attention. We'll go back to our initial kind of like LSTM thinkings. Say we're doing some kind of language modeling. We're trying to predict the next word based on previous words. The idea is that you have some words in a sentence, and these implicitly have relationships between themselves. So instead of using a lookup token from a separate set of features, like for example, in our French example, our features were a kind of like a feature database of the embeddings of our French words. We can use something called self-attention and use lookup tokens from the same input. So we're essentially computing these keys and these queries within the same sentence. Instead of looking up a different database, we're using our sentence as our informed database. The idea is that words in a sentence will implicitly have relationships between themselves. So in a single sentence, we can find a representation that's meaningful based solely on the information that we have. When we're decoding with an RNN, we use additional information of other token features that we've previously seen in the sentence. But this also leads to its own kind of set of issues, right? In comes the transformer. And this is a way that we can use self-attention and something called multi-head self-attention to come up with mechanisms to attend to different parts of our sequence. There are some problems with RNNs, right? We know that this is sequential, which means that we need some sort of previous state to calculate our current. This isn't very parallelizable because we have to go in order, right? From left to right to come up with a future state based on previous states. This makes it bad at capturing long sequences. So the amount of compute steps needed to capture the relationship between Ti and Ti plus D scales linearly with D. If I have some input at time 0 and some input at time 5, I have to go through every step 1, 2, 3, 4, and end at 5 to get those connections. We need to run the RNN D times to get from one step to the I plus D step. And in that time, you might forget the Ti, depending on how long those connections are, right? Ti could be at 0, Ti plus D could be at step 100. And there's no guarantee that my gradients are going to maintain throughout this process, right? We've talked about these problems before. And this leads to RNNs having lackluster performance depending on sequence length, which isn't ideal. Attention is all you need was a paper by Vaswani and a couple other authors. What if we got rid of recurrence and we use self-attention to model sequences, where we can use the information contained in a certain sentence or kind of groups of tokens that are present in our sentence to come up with some kind of informed way of weighting different parts of our sentence. On the right, we can see a single transformer layer in a transformer model. And this consists of three main parts. We have a multi-head attention block. We have add and normalization layers. We have a feed-forward network. And then we have another add and normalization step. As you can see, there's some connections between our inputs and our outputs. And this is where we are taking in information from our inputs. And we'll kind of dissect these and talk about why these are important, each step. Our inputs are similar to before. We have a sequence of token embeddings and positional embeddings. And we want to use those to apply self-attention. A quick overview. We have an input sentence, the big red cat, an input representation where E is our set of embeddings and our input. We want a transformer layer, which is represented by this architecture over here. And we want to generate a set of output embeddings. This is our problem. In this example, we're going to be looking at next token prediction. Now, for example, we want our next output to be the word jump. The big red cat jumped. And that is correspondent on our output representation. At a high level, for each token representation, we want to augment its representation based on its relationship to other tokens. What does that mean, right? We want to allow the model to focus on different parts of our input sequence and compute multiple attentions in parallel, and then use that information to determine what is most important. Our input sequence is transformed into multiple attention representations, and we want to focus on these token-to-token interactions in each representation. We have different heads, which all they are linear projections that operate in parallel, that apply attention representations, and they capture different aspects of context. Next is our add normalization layer, which we'll talk about, as well as our feed-forward network, which applies nonlinear transformations to our data, which, as we know from previous lectures, is kind of the main purpose of certain feed-forward neural networks. How does self-attention work, right? Can we predict a period at the end of this sentence? The big red cat, period. Or do we want a verb? Maybe this sentence isn't complete, and instead of a period, we want to predict a verb like jumped, right? The big red cat jumped. How do we know what to do? When we do a prediction, how can we figure out what the next step is? We can potentially look at, were there verbs previously in the sentence, right? This is information contained in the sentence itself. If we haven't seen a verb yet, and we know that sentences generally have verbs, then it's more likely that our next token is going to be a verb than, for example, just ending the sentence with a period. In reality, attention weights tend to be a little harder to interpret, right? This isn't exactly how self-attention works, where we're looking to see whether we've seen a verb in the past, or we've seen X amount of nouns in the past, et cetera, et cetera. This is like an oversimplification to kind of gauge how this process works at a high level. We want to, in reality, repeat this many, many, many times and develop these implicit representations to come up with probability distributions for what the most next likely word is. The takeaway is that self-attention model, they model relationships in a sentence based on the interactions between tokens in the same sentence itself. We can think of this again as our database lookup. We have a key, we have a query, and we have a value. And what we want to do is we want to compare a certain query to every other key, right? Based on their respective keys, we want to calculate the importance using a dot product and a softmax to determine a probability distribution almost, as opposed to which keys are most similar. And then we want to select and combine the values of the most relevant tokens in a weighted sum. And that gives us a final weighted representation of which parts are most important. And this becomes a new representation of that token. All we're doing is we're taking a token embedding vector and we're multiplying by some matrices, WK, WQ, and WV, where we have simply matrices that we're multiplying together to do this dot product operation. This is simply a linear layer without the bias term, but that's something that we can include. And I think the visualization will make a lot of sense. So we have some sort of input representation. We have weight matrices, right? WK, WQ, WV. And we can apply a linear layer to get these initial values from our input embeddings. Now, each embedding has a respective K, Q, and V, where we have a key, a query, and a value. And this value matrix, you can think of it as our output from this dot product operation. Our query represents our embedding, and the key represents what we're comparing or what we're looking up from other parts of the sentence. We want to find the most relevant token based on Q. So looking at our first embedding of we can take the query that corresponds to it, and we take the similarity between that query and every other key that we have. Each token attends to every other key in every other token. And the connection between arbitrarily long inputs is O of 1, right? We don't need to go through every single step. We don't have to run this process 500 times to get to the 500 token, right? All we have to do is take our current query and multiply it with the key of the 500th token. And now I have a similarity score, right? That took O of 1. It's a constant operation because I have keys for every single token. We take the dot product between our Q and every other K in our representation. This results in a softmax distribution based on the magnitude of the dot product values. In this example, my similarity is closest to the key of my first word. Now I want to reweight every value based on that softmax distribution. So I'm updating my value score. We want to sum our reweighted values. And then we can scale these dot products. Does this make sense? This is one of the most important parts of attention. We want to take our query, we want to find its similarity to all of our keys, and then reweight our values. And that's the interaction between our key, query, and value matrices, if that makes sense. Scaled attention is the concept of scaling dot products by a factor of 1 over square root dk, where dk is the dimension of the key embedding. The only reason we're doing this is we know that dot product values can grow large as our dimensions grow higher, right? Implicitly, like the size of these matrices are getting bigger. We have higher dimensions, means more data, more information. And so some components of softmax can have extremely small gradients. As our values get really, really big, the difference in our softmax distribution between like peaks and valleys can get really, really big. And that can result in extremely small gradients. Dividing by a kind of like normalization factor that's proportional to this dimension allows us to, implicitly take into account that this phenomenon might occur. Multi-head attention is the concept, like I mentioned, of creating multiple attention representations called heads that operate in parallel. So we're projecting each key, query, and value triplet down h different times with different projection matrices. So now we have h different kind of starting values or heads of our KQVs, and we're doing this process h times. We process each head independently in parallel, then reconcatenate all of these values at the end and reproject them to get the final embedding. The idea behind this is that by doing this with multiple heads, each head can capture different aspects of the content and result in a more well-rounded kind of feature selection at the end. Multiple heads provide a way to model different representations of the same token and consider all of them together. That's why, as you can see, multiple head attention, multi-head attention has different input values, kind of representing that we have multiple heads that combine into one output. Next, we have an add and norm block. This is an add and normalization layer that takes the output from all attention heads that is summed element-wise with the input sequence. And we're adding the input sequence to this add block, right? This is a residual connection, which, we've talked about ResNets before. We want to include our input in our add and norm block. Specifically in the add component to remedy the vanishing gradient problem. Implicitly, we're having a lot of these layers. We don't want our gradients to get extremely small. So by adding our input in, this is very akin to ResNets. Next, we want to apply a layer norm, right, which is very similar to batch norm, but now statistics are calculated for each sample with respect to the parameters in each layer. You can think of this as a way to normalize kind of activations within a single layer across features for each individual example. So we're normalizing each feature in a single example independently. And this can have learnable parameters as well. This is very common in RNNs and transformers to improve training and just overall generalizability. Next is the feed-forward block, which is simply a feed-forward neural network, two-layer MLPs that are applied individually to each token embedding. And then lastly, we have another kind of like add and norm block at the end, which again takes into account the input kind of in a residual fashion to remedy vanishing gradients. All this MLP does, kind of going back to the feed-forward neural network, is it adds nonlinearity to our output. All right, so we know that we want to sum the reweighted V's based on which key is closest and our resulting kind of distribution. And then this is simply a visualization of the process that we talked about. We apply our residual and our layer norm. This is like the add plus layer block. We apply our MLP to introduce nonlinearity, which is pretty akin to just a position-wise, like feed-forward one-by-one convolution to generate final values for each of our tokens. Then another residual and layer norm to get our output. Something else that we can consider is position embeddings. We can note that the architecture described isn't inherently sequential, right? We're basically just taking the embeddings for each of these. We're doing our little KQV, and then we're reweighting these values. But where does the sequence of the sentence come in, right? We're relying on our sentence to kind of implicitly find these relationships. Everything attends to everything else. A solution is to append position embeddings to the input so that each token can keep track of its index in the sequence. We can use a couple different ways to do this. Sinusoidal embeddings or learned embeddings are two ways. We're not going to get too into that, but keeping into account or taking into account positions can be important. A CLS token is a way to do this, right? We can have a dummy token attached to the beginning of each input and use the output representation of that token for classification. This input, you can think of it as kind of tagging along during this process. This is a classification token. That's what the CLS token stands for. And it's used in models like BERT, for example. We're inserting a token as a unique token at the beginning of our model to signal kind of where the start of a sentence or the start of an input is. After the pre-processing and tokenization and stuff, this CLS token becomes the first token in our output. And it has a corresponding output representation in the model's like hidden layers. This can be used for a variety of downstream tasks. For example, in a sentiment classifier, we can pass our CLS through a feed-forward neural network with a softmax at the end to predict positive or negative sentiment after passing it through our transformer model. Now, going into the math. We know that we're multiplying our query matrix with each key of every other token in our sentence. We have Q input, K input, V input, which is the QKV for each input, and we're multiplying simply the dot product for each token. This process is simply a matrix multiplication. We result in a value matrix where each I is each Q and K dot product, right? This is simply a batch matrix multiplication operation. Now we can treat these as weights by applying a softmax to these to get some sort of weight matrix where these are now normalized, and then simply multiply that weight matrix by our value matrix. And by doing one more matrix operation, we have, voila, our weighted sum and updated values. So we're doing this kind of matrix operation, another multiplication to get our final values. This is simply taking into account kind of like our matrix form. Attention using Q, K, and V is just a softmax of our Q times our K transpose. And again, we talked about our scaled attention where we're dividing by the dimensionality of our embedding to kind of prevent vanishing gradients. And then we're multiplying that result by our value matrix. It's as simple as that. And in multi-head, we're just doing this across multiple heads and then combining them at the end. We can notice that attention is really just large matrix multiplications. And this turns out to be a lot more computationally efficient than other solutions. Even though there's a ton of operations, right? We're doing an order of n squared operations. These are super parallelizable on GPUs and TPUs, right? We've learned that deep learning is all just matrix multiplications. And that's all we're doing here as well with the QKV process. There are different kinds of architectures that we could have. Like other sequence models, we have encoder models that just produce embeddings. How many of you guys have heard of BERT before? Have any of you guys, by show of hands, like used BERT before? Nice, okay, cool. Like I mentioned, BERT it was developed by Google, and it allows us to do both like sentence level embeddings, individual like word embeddings, but we're able to produce a set of embeddings from input tokens. So instead of just doing like a naively mapping of, for example, each word in a sentence to like glove embeddings that are 50 dimensional, then just taking like the average of that as a sentence level embedding, we're able to take a sequence of input tokens and generate one cohesive embedding that hopefully captures more information and isn't as lossy as input as just like an average of embeddings, right? Which inherently loses information and it has no weightage of information. Decoder models, on the other hand, we don't want to use future tokens to decode the current token because we don't have access to those, which results in something called mask attention, where we ignore future tokens during training. So we don't calculate like similarities with future tokens that we may not want access to. And we only use like past tokens. So we have a mask that's moving and slowly getting unmasked as we go through a sequence. This is an example of how GPT and other like large LLMs work. These are decoder models, right? Like other sequence models, we can have encoder-decoder models in any sort of like sequence-to-sequence task. Cross-attention is where queries come from previous decoder layers, but keys and values come from your encoder output. So you're taking an encoder with keys and values, and our queries come from the previous decoder representation. This is an example of this would be kind of implementing attention mechanisms in RNN models where we have some sort of like implicit sequence and encoder-decoder representation. Revisiting the problems that plagued our RNNs. Did we end up with a solution? We had issues modeling long sequences, right? Everything now attends to everything in a transformer. And that means there are constant operations for arbitrary distance between tokens. With an RNN, if I had a 0 and 500, I have to run my RNN 500 times to get to that token because it depends on the state of the previous kind of representation. However, with this transformer architecture that uses attention, I can simply take the query at step 0, and multiply it with the key at position 500. That's a constant operation. And now, instead of sequential, we have parallelizable matrix operations that can be done in batches. And this is very efficient across GPUs and TPUs. So we have solved a lot of the problems that are present in RNNs. And that's why transformers are so important and powerful in today's kind of topology of neural networks. Transformers are a very general architecture, which is why we used a lot of language examples in this presentation, right? This is a class on deep learning for visual data, but transformers are generalizable through like text inputs, through really any way that we can model sequences, which is why this lecture was a little more broad and less computer vision specific, right? We did talk about squeeze and excite networks, which hopefully, tied into how these can be used. But, transformers can be applied to computer vision. We'll talk about this more in our next lecture in vision transformers. And it doesn't encode very many inductive biases. It doesn't assume that there's any special thing about our data or any special like patterns or representations beforehand, right? Unlike RNNs and CNNs, which impose sequentiality and translational invariance, right? We've talked about how CNNs, by their nature, we know that they have certain architectures that are more conducive to images, right? RNNs impose a kind of like a modem of sequentiality. Transformers, on the other hand, you just have a sequence of tokens. We don't care whether these are image tokens, whether these are text tokens. We don't care what they are. We just have some long input that we want to learn about. And that's what makes transformers so powerful, right? Somebody once said specialization is for insects. What we're trying to do is generalize as much as we can, right? As humans, we generalize. We take things in one domain, we apply them to another domain. Our models should be able to do the same. And transformers are kind of that happy medium. That's it for today. This is the lecture attendance code. We do have a tiny URL. So feel free to please fill that out now if you can.